Solenoid. A solenoid is a length of wire that is formed into a helical shape with a current passing through it. So let's look at the picture here, and here's what I mean by helical. Keeps wrapping around, okay, and then comes out the other end. This geometry gives rise to a very strong magnetic field within the helical wire that can be turned on and off by switching the current on and off. The solenoid below, and get rid of the markings here, shows the wire wrapped around an iron core, a ferromagnetic core. The solenoid functions as an electromagnet, and it is used in automotive ignition circuits, pinball machines, dialysis machines, locking mechanisms, and water and airflow regulator. The ferromagnetic properties of the iron core, this thing in here, can increase the field by 3 orders of magnitude. So that means 1,000 times. The magnetic field generated by the loop of wire causes the magnetic domains, talked about them back in the magnetism unit, in the iron to line up. That reinforces the field created by the current. If the loops are closely spaced and the solenoid is not very long compared to the radius of the loops, then the magnetic field generated by the current resembles that of a bar magnet, and it equals the vector sum of the magnetic fields generated by each loop. So what you have, if we have a short solenoid, let's call this one, got the magnetic field lines going out like that, coming back around, and they're closely tied into the solenoid because of the geometry, and that looks like a bar magnet. Okay, so here's your north and south pole, just like a bar magnet. However, a more practical usage is something called an ideal solenoid. We will extend the length of the solenoid, and the length is much greater than the radius of the loops. We now have an ideal solenoid. As the length-radius ratio increases, the field becomes much more uniform within the solenoid, and we'll show that, and gets much weaker outside the solenoid. That's what we're going to deal with here. So picture this. Here's your solenoid. Let's say it's very, very long. Inside, you're going to have tightly packed, strong magnetic field lines, uniform. It's constant anywhere within the solenoid. Then, as you know, it has to loop around, right? You have to come full circle. What happens here is there's one of them. The next one will be further out, and we'll show why that works, until you have a very small flux density outside. So the magnetic field at any point is very close to 0. And that's what we're going to work on now. Let's start analyzing the ideal solenoid. We have a schematic. This shows a cutaway view. So the picture that I was kind of scribbling on the last page looks something like this. But if you then slice it, you look at, okay, so here's the loop going around like that. It's hard doing these things in 3 dimensions. But we have the current coming out of the page here, connects to this wire, where it's still the same wire. It then goes into the page, wraps around the core, comes up here, comes out again, comes to the next point, goes in, comes out, goes in, and it just continues wrapping around. Okay, so hopefully you can see that. And what we're going to show is as the length of the solenoid increases, a similarity to a bar magnet decreases because the external magnetic field shrinks. So let's see, did we get everything here? Yep. So there's your current flowing, and we've already sketched in the magnetic field lines. And this is kind of telling you what we're going to come up with. They're uniform inside. That's a constant magnetic field. Create 2 Amperian loops on the solenoid. Loop A, over here, will be used to determine the magnetic field outside the solenoid. You can see it's just encircling the wire that starts the solenoid there and wraps around, and doesn't include any other wires or any other pieces of the wire because it's just one long wire. Loop B will be used to determine the magnetic field inside the solenoid, and that encloses all those wires, and you can see it has 4 sides. This side is totally outside, this is totally inside, and this guy crosses the boundary. So notice the Amperian loop is not a circle this time, it's a rectangle. Right? For Gauss, we always had cylinders and circles and spherically symmetric things. Here we have a rectangle. Loop A is actually perpendicular to the page. That's kind of tough to see. but the current passing through it is just due to the small current moving from left to right through the helix. So let's just show what that is. If it's perpendicular, which it is, we say it's kind of like that. So the current clearly is flowing from here to here, okay? But that's in the plane of this page, so it's really not going through the loop. But then what happens? This has to go over a little bit to the right to get there. So let me just erase that again, just to make that really positive. So here's our Amperian loop coming out of the page. This circuit, this current goes like this, and then it starts coming up and crosses through the Amperian surface to go up there. So that loop only encloses a tiny bit of the solenoid's current. Yes, it's the same value of I, but if we take an Amperian loop here, you have to count every single one of those I's, so it's multiplied. Here, you just have one I going through. So your field will form small circles about the loops at either end of the solenoid. And let's show that. Right, because if the wire, if the current's going this way, going to the next one, it's going to have a little loop of loop of the magnetic field like that. So you have tiny circles, tiny magnetic fields at either end of the solenoid. Loop A came out of the page, but loop B is in the plane of the page. Ampere's law will be applied separately to each leg of the rectangular loop. Let's look at sides 1 and 3 first, and let's check out 3. Okay? What's the magnetic field generated by this guy right here? Okay, it goes counterclockwise, so at this point on the Amperian loop, it's in that direction. Okay? So what do you know about that? If we're integrating around the Amperian loop, and let me just make this a little bigger here. Here's the Amperian loop. And here's our little, let's just put the wire here. It has a magnetic field going around just like this. Note that that's the direction of the magnetic field. So at this point, it's going like this, horizontal. So that's B. What's ds that I'm integrating? It follows the path. There's my ds. ds is perpendicular to B. So therefore, the dot product is 0. And you get a similar thing over here on side 1. So sides 1 and 3 does not contribute anything. So B, the integral, the line integral of B dot ds, well, B dot ds itself is just 0, so the line integral of that piece will be 0. 1 and 3 contribute nothing. For side 2, we can place the side, that's this side over here 2, we can place at a far distance from the solenoid. The B field at that point is essentially 0, as was just shown with the Amperian loop A. So the path integral for side 2 is 0. We are left with side 4 over here. Now we're inside the solenoid where the magnetic field is uniform, and it's all in the same direction as ds. Okay, because ds is over here, right? There's ds, and all the magnetic field lines are in the same line. So what we have is B dot ds will reduce to BDS. The right side, what current are we enclosing? So you might just say I because that's the current through the solenoid, but each time one of these loops goes through the Amperian circuit, we count it again, okay, through the Amperian loop. So if it goes through n times, and that's what we're going to say, n times inside that loop, the total enclosed current will be n times I. So what do we have? Just one last thing. The path integral for ds, where we go from here to here. Okay, again, let me erase some stuff. We go from here to here. We integrate. We add up all those little pieces of ds, and what do we get? The length of the Amperian loop. So we have BL equals mu 0 n times I, divide out, and here's our magnetic field within the conductor, within the solenoid. After all that work, we found that the magnitude of the magnetic field inside the solenoid is equal to the field found by performing the line integral on segment 4 right here. The line integrals for 3, 2, and 1 wound up as 0. So we have this equation, and we're going to go ahead and define little n as the number of loops per unit length, or big N over L, and we get B is mu 0 n times I. Note that for anywhere within the solenoid, the magnetic field is constant. It doesn't matter if you're over here, or even what the width of the solenoid is. It's always mu0n times I. And again, this is for the ideal solenoid where the length is much greater than this distance here, the distance between the two pieces of the helix, over there and there. The width of the solenoid, in other words. As always, we like to relate this to some other knowledge we have. Earlier, we found that a capacitor produces a uniform electric field between its plates. We now have a solenoid producing a uniform magnetic field within its helical shape.